What's up, guys? Today we're going to be looking at current, electrical current. So I feel like most of like physicists and scientists who are beginning to study physics, or students who graduated out of high school, they really don't understand how electricity works and what electricity is actually used for in a circuit. So yeah, I'm going to sort of give answers to few questions that students would have, and I'm going to clear out the concepts both theoretically and practically. That's the important thing that we are going to look at. So yeah, let's get started. So first, let's start off with what sort of the basics. What is current? So current in general as a word is basically the flow of anything. We have wind current, we have water current. Those are all just flow of any particle. So electric current is basically the flow of any charged particle. It might be positively or negatively charged. For the sake of simplicity and for beginner stuff, we're just gonna look at metals. Okay, any circuits made of just metals, because when you come to semiconductors, it's a whole new other discussion, because there we have to consider both positive and negative during electrical flow. But then here in metals, we just need to consider just the electrons that are flowing. So yeah, let's get started. So now we're going to look at conventional and unconventional current. So basically, what conventional current is that it's the flow of ions from positive to negative direction. But in reality, in a conducting metal, the actual electricity is from negative to positive. That's non-conventional current. That's actually the real direction of the current. So let's look at it by taking a simple circuit. Uh, so no, this be the we are going to consider only DC circuits, right? For the purpose of simplicity. So what we have here is a simple DC circuit. So this is the voltage source, and this is the resistor. We can keep it as R, and this is a device. It's a bulb. And, yeah, so yeah, in conventional current, the current flows from positive to negative. So the current is eventually the electrons are flowing through the resistor to the bulb, right? But then in actuality, the electrons are flowing first to the bulb and then to the resistor. So you might have a question, right? In practical cases, then of course we don't follow conventional current, right? We follow the actual direction of the flow of the current. Then only we can accurately place the resistor in order to get the accurate values. But in reality, that's not true. In both in practical and theory, we consider conventional current, and to understand the answer of why we exactly do that, we need to first look at a law, right? Uh, yeah. So basically, we need to look at Ampere's law. So basically, Ampere's law states that the line integral of the magnetic field around a closed path is proportional to the total electrical current. So to understand this, we need a diagram. So let's take a conductor, like a metal conductor, kind of like pipe or a rod, right? And then what it's eventually stating that if there are magnetic fields, like circular magnetic fields around this conductor, you know, and let's take the direction of the let's take the direction of the magnetic field anti-clockwise, and we need to use right hand thumb rule. Basically it's like a screw basically. um, so what you need to do is that it's flowing in this direction, right? That is a way of representing a magnetic field through symbols. So basically you just represent it through cross symbols. So these cross symbols mean that right here the magnetic field lines are penetrating through the plane, whereas dotted dot means that it's penetrating out to outside the plane, out towards us. So basically the magnetic field is sort of like it's coming out of like this and it's going like behind that and making a full circle. So basically what this states that using no now we can use the right hand screw or thumb rule to find the direction of the current. So now we now found out that the current is moving up. So this is the current. So yeah, now what this basically law states is that the line integral of the magnetic field, all the magnetic field, basically now we can take the length of the conductor as L. And now what this law is basically stating that if we take every single magnetic field line, basically it's a circle, and then integrate everything. Like we are basically adding all the magnetic field from 0 to L, we will be getting this value. Basically, this is a constant. This is a permeability of free space. So this is acquired by when a magnetic uh, field is present in free space. This is the constant that we get. So yeah, and then into I'm sorry, we'll get I. I'm sorry for that. We'll get I. This is current. So basically, what this law is saying that if we have magnetic field or field lines in this sort of arrangement, we will be getting a specific value of current inside the conductor. So now, if we flip that law and make it into opposite, then intuitively we'll be getting that when a current is flowing from 0 to L in upward direction, we will be getting a magnetic field like this. So in this way, we can basically sort of prove that uh, current produces magnetic field. So yeah, this is very important to understand why. This is basically important to understand why we only use conventional current, because what you need to understand is that when we are making a circuit, you know our goal is not to not to make the current flow to the device. The current itself on its own does not give power to the bulb. Our main goal of a circuit is to transfer energy from the source to the bulb, right? So current in itself is not energy, but it helps to make the energy flow. In that the goal of a circuit is to transfer energy from the main source to the device that we want. Power is basically the energy transferred per second. Basically, it's the form of energy when it's flowing, when it's getting transferred. Um, so to really understand how energy is transferred, we need to look at something called pointing vector. So pointing vector is represented as S vector, and this is derived from Maxwell's equations. So yeah, yeah. So it's basically one by permeability, constant of permeability, and then we have electric field cross magnetic field. Yeah. So basically, what this represents is the direction and magnitude of the flow of energy in electromagnetic waves. So basically, you might ask, how is electromagnetic waves? How are they produced in the circuit? So of course, we have in a simple circuit, we have the voltage source, which produces EMF, which is electromotive force. This electromotive force in a simple circuit is produced by electric field, right? So this electric field is being produced. This electric field, gives energy to the electrons, and the electron moves, right? So when the electrons are moving, right? When the electrons are moving, we have seen by Ampere's law that it produces magnetic field. So yeah, the circuit produces electromagnetic field. So you know, yeah. So the electromagnetic field is produced, and basically electromagnetic waves is basically the fluctuation of the field. So now we know that there is electromagnetic field present all over the circuit. Now, basically, all we need to do is to transfer energy from the source to the bulb, and this is in the form of electromagnetic fluctuations, like electromagnetic field fluctuations. Now, now wherever you place the resistor, right? Wherever you place it, I place it here. But wherever you place the resistor, the amount of electrons flowing through will decrease. So when the number of electrons flowing decreases, of course, the magnetic field produced at that place decreases. And now intuitively we can guess what's going to happen next. So basically, at this is the the energy, energy in the flowing state. So basically, here at this point, the resistor point, it decreases. So decreases, and there is a total of S net over all over the circuit. So basically, it's sort of like equally distributed all like throughout the circuit. And to kind of maintain this equal, equal distribution, when the energy at a particular point decreases, energy from other points of the circuit equally gets displaced to that area in order to maintain sort of an equilibrium. Basically, what I'm trying to say is the energy that was supposed to go to the device would go to the resistor rather than going to the device in order to maintain stability, in order to maintain equilibrium, right? Yeah, basically that. And then you intuitively think about it, right? Let's look at a picture. Let's look at a picture where electric current is the main is the only factor of energy transfer. If you look at it in that case, we have to consider the drift velocity of electrons. Once when a potential difference is created by a voltage source, an electric field is acting on the electrons, the velocity of the electrons will approximately become 10 to the power minus 3 meter per second. And how can you explain that speed with the speed of the actual current that in practical cases? So I'll show you a demonstration of how quick electricity or the transfer of energy is. The transfer of energy is, you know what I'm saying? Electricity in itself is slow, but the transfer of energy is fast. I'll turn off the light and show you how fast it is. Instantaneous. It's instantaneous. Once when you click it, instantly that there is the energy is cut between the energy flow is sort of cut, and then once it's turned on, the energy, it quickly reaches the device, the LED. So how can we sort of explain that other than using electromagnetic waves? Electromagnetic waves act, and they are as fast as the speed of light. They have the velocity of the speed of light. So the fluctuations of the electromagnetic field is in the speed of light. So that's why it's instantaneous rather than taking forever for the circuit to work. I'm trying my best to use the words correctly. Like, I would have used, power, like I would have used a sort of term where, we need power for, the bulb or whatever. But that's not actually the case. The power is basically the flowing form of energy, basically. But I use it sort of in a more of a philosophical term at that time, where, power, and intuitively we think that power is a source that makes something, something. Intuitively we think of power as a sort of strength, so that's why I might have misplaced that in actual energy. So basically, all you need to remember is that this voltage source that creates a potential difference, that creates an electric field, that in turn moves the electron, which produces a magnetic field, and that now there is both magnetic and electric field. So combined, it becomes a electromagnetic field is formed throughout the circuit, and the transfer of energy is taken place through the fluctuation of electromagnetic field. So yeah, and power is basically the form of energy that's the flow state of energy, basically. Now you might have noticed I've explained both power and Poynting vector as a flow state of energy. So I did some research and I found out that we can actually relate the both, as one formula. So basically, power is equal to double integration. I think it's area into Poynting vector dot dA. Think so. I think so. I think so. Yeah, I'm correct. It's basically dot product of two vectors. Yeah. So yeah, this is the total view. Basically, in practical cases, we use conventional current because we don't require to use the actual current in order to make a circuit work. And this is why. So, however bad conventional current might be. This sort of way of thinking actually helps you to understand how current, or like how current is used in a circuit. Current is not the main thing. It's not the actual transfer of energy, but it helps in the transfer of energy. So I feel like I'm grateful for conventional current to confuse my brain up to get to this conclusion. So yeah, I hope you guys understood. Uh, and if you have any doubts, leave it in the comment section down below. If you want me to explain any other concepts, leave it in the comment section down. Anything, if there's any mistakes that I've done, or like if if there are any places that I can improve on, please leave it in the comment section down below, because this is my first ever video that I'm actually explaining real physics concepts, not just philosophy. uh so yeah, hope you guys enjoy. Peace.